in this segment, and we'll discuss the string functions. Now, the string functions offer various operations on char, varchar, or text data. If you thought the numerical functions were a hodgepodge, you should see the string functions. There's lots of duplication and not a whole lot of rhyme and reason. Still, they get the job done, and the easiest way to explore them is to look at how to do various common jobs with strings. So let's start with getting the length of a string. That sounds like a simple enough operation, but there are at least 5 string functions for it. So question 1, just as a quick exercise to get you looking at the docs, find 5 functions for string length in this MySQL documentation here for string functions. Don't try to make sense of them. We'll talk about it in a moment. Coming back from a pause there, we've got, well, there's char length here, and character length, and bit length, and a little farther down there's octet length, and just to be complete, there's also length. So what were they thinking? Why do we need 5 of these? Well, first, there are 2 synonym pairs, character length and char length, and also length and octet length. So it's really just 3 length functions, but that still sounds like too many. So let's look at why all 3 variations are needed. First, if you have a string holding 16-bit Unicodes, then there's a difference between length measured in characters, which would be supplied by char length, and measured in bytes, as would be supplied by length. Languages like SQL that support multi-byte character representations have to draw a distinction between length in bytes and length in characters. And it gets even more complex when you consider encodings that vary in length per character, like UTF-8, which uses 1 byte for ASCII characters, but uses escape sequences of up to 4 bytes for higher-numbered Unicode characters. For such encodings, there's not even a constant factor relationship between character length and byte length, so we need different functions for the 2 meanings of length. And then second, SQL's complex type representations sometimes use partial bytes per symbol. Decimal, for instance, is a good example of that, 4 bits per symbol. This makes it useful to know the exact number of bits in a piece of data, which number is not always divisible by 8. And the bit length function, which works on any type, not just strings, supplies that. And you'll have to put up with another brief historical aside here. Why is the length synonym octet length instead of byte length? A byte is an octet, right? 8 bits? Well, today, yes, but in the early 1970s, there was still some debate about that. Byte meant number of bits needed to store a character, or smallest group of bits fetchable from memory. And there were machine architectures with 7-bit or other byte sizes. Octet was thus a more precise term than byte. Now, the next major category of string functions is string comparisons. You can, of course, compare strings with the standard relational operators, thus. But just to be complete, there's also strcomp, a function that works just like the C and Java methods that compare 2 strings. So if I do a strcomp on 2 strings thus, and you get a -1 if the first string is smaller, a 0 if they're equal, and a 1 if the first string is larger, as in the case here. Now, if you're like me, you may have found that -0 positive rule I just recited hard to remember in any of the half-dozen or so languages that use it. A good mnemonic is that strcomp of str1 and str2 is analogous to a subtraction. If the 2 strings were numbers, then str1 minus str2 would be negative if str1 were less, and be 0 if the 2 were equal, and be positive if str1 were greater. Now, why use strcomp if relational operators will do? Because it does all possible comparisons in one pass, leaving you with an integer that you can quickly test for different conditions. And this can be more efficient with very long strings. The strcomp function also has another one of those special syntax keywords illustrated right here that let you specify the collation order, or just the collation in MySQL speak. Recall from earlier discussion that the sorting order of characters varies per nation. So if I add at the end a collate and then one of various possible collation orders, I can get the comparison done on that basis. And you won't need this if you're working purely in English, but SQL has a lot of support for internationalizing strings in their collation order and so forth. SQL also offers pattern matching comparison functions and operators, which we'll briefly review here. And as usual, you're welcome to explore them on your own if you want more detail. Now, we've already seen the like and not like operators in where clauses earlier on. There are also regexp and not regexp, which work like their like cousins, but with full regular expression pattern matching. If you're up on your regular expressions, those may be useful. And like many recent database management systems, MySQL now includes a powerful indexing and searching system for very large text strings via the match operator. And perhaps the most interesting string matching operator is sounds-like, which uses the soundx function to produce a standardized phonetic interpretation of two strings and returns true if the phonetics match. Let's try that out here. There's a select, and I'm doing a soundx 2 and 2 and 2, and as you can see, they all produce the same encoded string, which is supposed to represent the sound of the words. Yeah, it doesn't work perfectly, and it's prone to say words that words sound alike when they really don't, but it's still cool. Okay, moving on to our next major topic here. Finding a substring within a string is a common operation, and SQL offers the inster, locate, and position functions for this. The latter two are synonyms, and they return the offset of a substring within a larger string, starting the search either at the beginning or at an optional initial offset. And if you aren't satisfied with that, inster will do the same thing, but always starting with or at the beginning of the string and with parameters in a subtly different order, thus inviting entertaining bugs. So here's an example of locate at work. We'll use that one as our main substring locator. Now this hunts for she in she sells seashells, and it starts at offset 3. And as you can see, it returns 15, which is the offset of the second she in shells. Retrieving a substring from a larger string may be done via subster or its synonyms substring or mid. And they all let you use conventional parameter syntax. For example, subster on sample string with 8 and 6 retrieves a string of 6 characters from sample string starting with the 8th one. And that would, in this case, be string in the example given. Conveniently, the the offset parameter may be negative, which is interpreted as an offset from the end of the string instead of the beginning. That's a nice feature you see now and then in string libraries. It saves a lot of care length calls when you're working from the end of the string. For instance, this call does the same thing as the prior one, but with -6 being referenced from the end of the string. Now, less conveniently, offsets are 1-based, not 0-based. So offset 1 is the first character of the string, and -1 is the last. An offset of 0 is reserved to mean not found for substring searchers like locate and position. Modern libraries would use -1 for not found. 1-based indexing is another one of those 1970s things. It wasn't until C became widely popular, actually, that everyone realized 0-based indexing was more natural for coding. And finally, if you're just getting a prefix, there's left, or just getting a suffix, there's right, for those who are too lazy to enter 3 parameters. And no string library is complete without a general find and replace function, and SQL's is replace. And you can check the details of all of those in the docs, of course. So do so, please, and answer question 2. Rewrite left, right, supercalifragilistic-43, I'll put it up here. Do that as a single string function call instead of 2 nested calls. And if you've done a bit of research, first, as you can see, that pulls something right out of the middle of the string there. And one way to do the same thing would be select subster supercalifragilistic -4, 3. Redo that correctly there, and you can see it comes up with the same substring from the middle. So question 3. Write a single function call using nested functions that translates a string into Pig Latin by removing the first letter and putting it at the end of the string followed by AY. And for the Pig Latin purists among you, don't worry about the hey rule. Just follow that one practice of first letter at the end and put AY after it. You may find the function concat useful for this. So one way to do that would be the following. We're going to do a substring of, say, sample, the word we're Pig Latinizing, and we're going to get the first two, or everything after the second letter, I'm sorry, the remaining part of the word, and then we're going to get the first letter of that and concatenate them together, and then concatenate after that AY, and end up with ampersand. Okay, next subtopic here are code and character translations. It's often useful to translate string symbols into their equivalent numerical ASCII or Unicode values, and vice versa. And the functions ASCII and ORD return the ASCII or Unicode value, respectively, of the first character of a string that's passed to them. So select ASCII of alpha will give you 65, the ASCII code for capital A. To get later characters, you're expected to extract substrings to pass to ASCII or ORD. And if you want to be really fancy with strings, function char lets you create a string from a series of numerical Unicode values and specify the character set to use as well. For instance, the string in Mandarin, ni hao ma, means how are you doing, may be constructed with this little select. The characters don't show on my particular screen here, but they would on another one. The first three arguments are the Unicodes for those three Chinese ideographics, and there's a special syntax at the end to designate the UCS2 character set. And then next section here, quick edits. There are a number of what might be called quick edit functions to do common string editing operations, and these have the usual surfeit of synonyms for removal of leading blanks, trailing blanks, or both, respectively. We have ltrim, rtrim, or trim. Synonymous functions, ucase and upper, will uppercase all the alphabetical letters or characters in a string, and from that you can guess what lcase and lower will do. Reverses a string, not that that's called for too often. More useful is repeat, which creates a string by repeating some other string a number of times, and if that's not convenient enough, space will create a string made of a given number of spaces. And there are a few others like this. You can look them up. And then a final important point here, the quote function and Bobby tables. The quote function deserves a section of its own. If you're not familiar with the concept of a SQL injection attack, or even if you are, I refer you to perhaps the most famous webcomic of all time, and certainly one of the funniest, at XKCD number 327. And there it is for your reading pleasure if you haven't seen it long since. So just let you read it for a moment there, and then let's talk about it. If it's not clear just what's wrong with little Bobby Table's name entry, consider a website that takes the name as entered and builds a small SQL script to insert the name into a student table. And we'll actually put that up here. So substitute, question 3 here, substitute into that insert statement right here the comics string. Robert, quote, drop table students, and so forth. And explain why it parses and what it does. And you may need to know that dash dash, like pound, is a SQL comment marker. So I'll clear the screen and fill that in with the substitution while you're thinking about it. Okay, if you've parsed through it, you should see that the result is, as we see here, and this will parse just fine with the final closing parenthesis and quote and semicolon neutralized as a comment. And then, of course, the inserted second command here will wipe out the students table. Now, This is a SQL injection attack. Do people do this? Oh yes. I personally know a student who got into hot water just for finding and reporting such a bug in a school website, which really is not fair since he was perfectly honest about it and did no harm. The solution here is to properly escape critical punctuation, especially closing quotes, in absolutely all user-entered data. And the quote function does this. If we use it on little Bobby's data and put a quote, I'll just put the notes up here, it's a little easier. And if we put a quote call on Bobby's data, right there, then that becomes insert into student's name values, and the quote will substitute out with, as you can see, the closing quote that's critical to the attack gets escaped, and it becomes part of the string name instead, literally in Bobby's name, as you might expect. And the result is that Bobby gets a strange and rather incriminating name, but no harm is done.